All right, guys, in this video, I'm going to tackle this problem right here. F of x is equal to 2x plus 9 over x cubed. What I'm going to do is I'm going to find the x-intercepts, y-intercepts, and any asymptotes, and then I'm going to graph it using my graphing utility. All right, so to start, the first thing I'm going to do is I'm going to bring my two fractions together. All right, I'm going to bring 2x and 9 over x cubed together into one fraction. So I'm going to find a common denominator. And a common denominator, a line of 2x and 9 over x cubed will be x cubed, right? So I can think of it, if I like, as this is 2x over 1. And so 1 goes into x cubed times x cubed times 2x is 2x to the 4. So I have 2x to the 4 plus x cubed goes into x cubed once. 1 times 9 is 9. And so f of x, written as a single fraction, is 2x to the 4 plus 9 all over x cubed. All right, so now I'm going to look for my x-intercepts, if I have any x-intercepts. So I'm going to evaluate f of x is equal to 0, right? So I'm going to let f of x equal to 0, and I'm going to solve it. So 2x to the 4, excuse me, 2x to the 4 plus 9 all over x cubed, that's equal to 0. Well, that means my numerator will be equal to 0. And so I have that 2x to the 4 plus 9 is equal to 0. Solving this, then I'll subtract 9 to the other side, and then we'll have 2x to the 4 is equal to negative 9. X to the 4 will be equal to negative 9 over 2, dividing both sides by 2, and therefore x will be equal to the fourth root of negative 9 over 2, and I'm taking the fourth root of a negative number. That's not going to be real, so that is not real. So what that tells me is I have no x-intercepts. My function will not cross the x-axis. So no x-intercepts. Now I want to find or test for any y-intercepts, see if I have any of those y-intercepts. To do that, I'm going to evaluate my function when x is 0. In other words, I'm going to evaluate f of 0. Well, f of 0 is going to be 2x to the 4 becomes 2 times 0 to the 4 plus 9 all over x cubed is 0 cubed, and I see that upstairs I have a 9 in my numerator, downstairs I have a 0, and I have a 0 in the denominator. That means it is undefined, right? So this is undefined. And because this is undefined, what that tells me is I have no y-intercepts either. So I have no x-intercept and I have no y-intercept. All right. The fact that I have no y-intercept is telling me then that I'm going to have a vertical asymptote at the y-axis at x is equal to 0. So let me just go through finding those asymptotes. Now that we have checked for our x and y intercepts, we can move on to our asymptotes. So now I will check for my vertical asymptote first. So my vertical asymptote, well, my vertical asymptote, I will check to see when is my denominator equal to 0, and any values that would make my denominator 0, I will omit those. So x cubed, well, if x cubed is 0, well then the solution is x is equal to 0. For what values of x is x cubed equal to 0? Well, x is equal to 0, 0 itself. And so sure enough, my vertical asymptote will be at x is equal to 0. That's just the y-axis. So x equals 0 will give me my vertical asymptote right there. Horizontal or oblique, well, I will have a look at my function again, and I'm going to consider the degrees of the numerator and the degrees of the denominator. If I look at f of x, it is 2x to the 4 plus 9 all over x cubed, and so the degree of the numerator is larger than the degree of the denominator. It's degree 4 in the numerator, degree 3 in the denominator. That large degree tells me I'm going to have an oblique asymptote, specifically the fact that the difference is 1, right? So the fact that the degree is 1 larger in the numerator than in the denominator, that tells me that I'm going to have an oblique asymptote. To find that oblique asymptote, what I'm going to do is I'm going to divide my denominator into my numerator. So let me just do that. So I'm going to find my oblique asymptote. I'm going to do that by taking my numerator, which is 2x to the 4 plus 9, and I'm going to divide that by x cubed, my denominator. So x cubed into 2x to the 4 goes 2x times 2x. So 2x times x cubed is 2x to the 4. I can subtract these. I will get a 0. I'll bring down my 9, and I'm done. X cubed doesn't go into 9, and so I have then that 2x to the 4 plus 9 divided by x cubed is really just, it goes in 2x times with a remainder of 9 over x cubed. We're considering the oblique asymptote. The asymptote tells us what happens as x gets large. Well, as x gets very large, we can see that this part here, my remainder, this here, as x goes to positive and negative infinity, this will go to 0. My denominator will get very, very large. I'll still have a 9 in the numerator, and so my function will go to 0 as x goes to infinity. And so my oblique asymptote then is simply 2x. What I'm left with is 2x, and that's my oblique asymptote. 2x, it is the line 2x. All right, so I can now make a stab at actually maybe just graphing this just right here, and then I will use my graphing utility. So I have, try that again here. And so I have 1, 2, and 1, 2 in this direction. And so just to put in my asymptotes, I know I have an asymptote. My vertical asymptote was at x equals 0, so that's this one here. And my oblique asymptote was 2x, so that is a line that goes through the origin with a slope of 2. So slope of 2 through the origin, well, that will look something like this right here, there, there. So it looks something like that. So that will be a line that looks, and I can go in this direction here and there, right? So that will be my oblique asymptote, positive slope of 2 through the origin. And so those are my asymptotes. And so my graph is going to be bound by those asymptotes, essentially. All right, let's actually have a look at what the graph looks like. So I've graphed it on Desmos earlier, and here it is. This is my graph with the asymptotes indicated, and there you have it. Right, so here and here, and sure enough, you can see that I have no y-intercept, I have no x-intercept, as we found. All right, just one final point about this this function right here is that if I was to talk about symmetry, even and odd functions, right? Well, clearly the function isn't even, but there seems to be a suggestion here that it's odd. So let's just confirm that we do in fact have an odd function. So what I'm going to do is I'm going to work out OR, lighter. I'm going to work out OR of negative x, and I'm going to compare it to negative OR of x. All right, so OR of negative x is equal to, our function with OR of x is 2x to the 4, so it's 2 times negative x to the 4 plus 9, all over x cubed, which will be negative x cubed. And so this is negative x to the 4 is x to the 4. So under my numerator, I have 2x to the 4. I have plus 9, all over negative x cubed. Well, negative x times negative x is positive x squared times negative x is negative x cubed. So that's negative x cubed. And so we find then that r of negative x is really just negative, bring that out in front, 2x to the 4 plus 9 all over x cubed. And that is equal to negative r of x. That is equal to negative r of x. So negative r of x is equal to, r of negative x is equal to negative r of x. And so therefore, our function is odd. We have an odd function. We have point symmetry across the origin, all right? And so, and sure enough, I think if we look, we can see that indeed we do have that point symmetry. It is symmetric about the origin. So just to point out that that function, this function does have some symmetry in it too. And that's it. That's that problem. That's how we go about it. Thanks a lot.